Welcome. Let us talk about query optimization this week. We need to understand a little bit more about query optimization aspects and start with the query optimization problem. The problem lies with picking up the best plan. Why? Because you develop many physical plan and you have to find the best physical plan which takes the lowest time to execute and get you back all the results. So if you see here, what happens, we have one kind of optimization we call cost-based optimization. What you do in this case is that you come up with a plans, and then you have different physical plan, but what you do, you need to prune the space of plans using heuristics. What I mean by using heuristics, you have some early knowledge about certain catalogs, number of records, and then based on that you decide which optimization is best. Sometimes you estimate cost for remaining plans because first of all you remove some of the plans which is going to be expensive, so you prune the space of plans, and then finally you estimate the cost. What is that cost? The cost is that simply the execution time. So you have to be smart about how to iterate through plans and pick the plan with the less cost. So remember one thing, in the entire process our focus is on queries with joins. So heuristics, what are those heuristics for pruning plan space? You have certain operations like predicates as early as possible. You avoid plans with cross product because you understand that Cartesian product is very expensive, and only you follow left deep join tree. Okay. Now take a look at this example. We have three physical plan. From logical query plan, we came up with physical plan, and then each plan has a cost associated with it. So P1, P2 up to Pn, these are actually different physical plans, and for each plan you have actually cost. For example, C1, C2 and Cn, and you are trying to locate the minimum cost which you are going to actually pick. So what you do, you review of notations. We have T of R means the number of tuples in R, and B of R means number of blocks in R. So a simple cost model could be like this. You take a natural join of R and S, finding the cost is nothing but remember the tuples of the relation R plus the tuple of the relation S. All other operators have zero cost. So the simple cost model used for illustration is basically the cost of the join operation is the total number of time it takes for the tuple in R and total number of time it takes for the tuple in S if you simply add them. So cost model, another example you see here, that we have in this, if this is a RA tree, you can understand relational algebra tree, and you have R and S, there is a natural join, so you add it, and finally take another natural join, so you are actually keep adding. So ultimately what is the total cost is the time for each relation that you have in the entire relational algebra tree. So there is another algorithm called Selinger algorithm. What it does, it is actually based on dynamic programming. And why dynamic programming? Because you are trying to find an algorithmic paradigm, you try to understand how to optimize it. So these are actually principle of optimality. Why principle? What is that principle? Optimal for whole made up from optimal for parts. So take a look at this principle of optimality. Here what we are trying to have a query and having a natural join of 5 relations. So 5 relation natural join is happening one after the other. Yeah. So that is an optimal plan. And now principle of optimality, how you are going to find out that one entire chunk is one optimal plan. Optimal plan for joining R3, R2, R4 and R1. And then once that optimal plan is done, then we have another join operation with R5. So you can bring it down further. Another optimal plan for joining R3, R2 and R4. So you are gradually coming down, and ultimately principle of optimality, you come into this point that, well, you can have relation natural join up to R of n is nothing but optimal for joining R1, R2, R3, and there are suboptimal for joining R1, R2, R3. So principle of optimality is giving you a chance to minimize your repetitive operations, and optimal why in a sense because we have the same nature of operation repeating over the time. So suboptimal join, again you can see here from R1 up to this, a suboptimal subplan cannot lead to an optimal plan. So Selinger algorithm ultimately is helping you in developing an optimal plan. So progress of algorithmic plan, it's happening from R1 up to different relations, permutation and combination of this join operations. So these are notations to represent actually optimal plan, like optimal R1, R2, R3 is colon cost of optimal plan to join R1, R2, R3. And if you see T of R1, R2, R3 means number of tuples in natural join of R1, R2 and R3. So Selinger algorithm, how actually it works, you see here now. That's what you're going to find out, the optimal of R1, R2, R3. You basically have optimal of R1, R2 plus T of R1, R2 plus T of R3, because that's actually suboptimal plan. So considering all three possible suboptimal plan, you find the minimum of this plan, which actually helps you to know the minimum cost plan. So it's valid for the simple cost model. There is another approach to the same algorithm, and you can see here you can have different path across this entire tree, but you can understand this is actually a different combination of R1, R2, R3, R1, R2, R4, combination of different relations, and ultimately you find an optimal plan. So more complex cost model depends on there are in the database management system, we have two join algorithm, tuple-based nested loop join and sort merge join, and two access method, table scan. There are two types. One is the join operation in terms of tuple and sort merge, and access means in terms of table scan or index scan. And cost is actually number of course, cost is number of Dix input outputs. So cost of a table scan, you can see cost B is a block of the relation R. That's actually cost of the table scan. But cost of the clustered index scan is like this, cost B of R, but this is an index scan. And of course, cost of clustered index scan, R dot A is greater than 50, you are looking for through index scan within the block of this cost. Cost of non-clustered index scan is cost of tuple of R, and it's actually the value becomes like this. So cost of tuple based natural join happens to be cost of entire plan, cost of outer plus you can understand the tuple of the relation X, and then ultimately cost of inner. So you basically have inner join and outer join, and altogether is a natural join coming into. So cost of sort merge join operation is happening to be like this. You have actually left and the right two different relation R1 and R2, and ultimately you have a condition to apply on R1, and then with this conjugate condition there is a sort, and finally merge. So what happens, the cost is cost for the entire plan is of course cost of right and cost of left, plus you have actually having a multiplication of the block xy within the 2, because there are two relation operation. So ultimately sorted on that, and there is another sort here, and ultimately that's the cost plan. So cost of the bottom line is the cost depends on sortedness of inputs, because if sorting is done it takes additional time. So principle of optimality works like this, and you basically try to find out that how you can actually minimize cost. So violation of principle of optimality, it may happen that suboptimal plan may be not actually optimal. In that case you may have to look for alternate plans, and principle of optimality actually is a very, very important. In this case you can see an optimal plan, but you may have optimality is lost. So can we assert anything about the plan X? which is maybe, so we kept principle of optimality happens to be like this. If plan X produces output sorted on R2A, then plan X is the optimal plan. If plan X produces output unsorted, then plan X is an optimal plan for joining this. So depends on what condition actually you're looking at in terms of principles of optimality. So these are actually interesting order. You basically have an interesting order in terms of group by operation, order by operation, So in case of SQL, you have different types of optimality, and there is a interesting order and example like select a star from, from a particular condition based on a condition. So there is a interesting order happens to be, different relation, different attributes, and putting a different condition together. So the modified Selinger algorithm works like this, that you have a different types of operation, and then based on which you have a combination of optimal plan, suboptimal plan, and finally you lead to the main optimal plan. So these are actually notations, optimal way of joining R1, R2, so that the output is sorted on the attribute R2.c, right? So these are actually conditional violation of certain optimal plans. And ultimate roadmap is the query optimization lies on the heuristics. You need heuristics. Why? Because you need to prune the plan. You apply Selinger algorithm and estimating the cost of the plan. So with this we stop here and we continue learning database management.